So as of now, we have discussed the Newton's first law and the second law, and also the free body diagram. Now in this video, we'll explore the Newton's third law of motion. But before that, we'll see a couple of problems related to the Newton's second law. So here a person throws a basketball of mass 0.15 kgs from rest and accelerating to a speed of about 90 miles per hour. Now we need to estimate the force exerted by the person on the ball. Now before calculating the force, we'll first calculate the acceleration. So I'm defining the coordinate system. So this is our coordinate system. This side we are taking it to be positive x, right? Now initial speed for the ball is 0 and the final speed becomes 90 miles per hour. Now if you convert this into meter per second, we'll get approximately 40 meter per second. So this final speed becomes 40 meters per second. Now what would be the acceleration? For that we can use the kinematic equations that we studied earlier. So we have the final velocity square is equals to the initial velocity square plus 2 times acceleration in the x direction times delta x, where delta x is the displacement. Now this is delta x, and from here this acceleration, the expression for acceleration will be equals to Vf square minus Vi square divided by 2 times delta x. Now we have the values of the initial and the final speed, but we don't have this delta x. Now from the figure we can approximate this value to be nearly 2 meter. We have to take this estimation, otherwise we can't able to solve this problem. Okay, so from here this acceleration for the ball in the x direction, this would be 40 square minus initial is 0, so 0 square divided by 2 times 2, and that is equals to 400 meter per second squared. So we have obtained the acceleration. Now to find the force, we're going to use the Newton's second law of motion, but before that I'm going to sketch the free body diagram. So this is a ball and the force exerted by the person on the ball is in this direction, this is Fx, and the acceleration of the ball is this much. Now from the Newton's second law of motion, we can write that sigma Fx, this would be equals to mass times acceleration in the x direction. So we have only one force in the x direction, that is Fx. So Fx is equals to mass for the ball is 0.15 kgs and the acceleration is 400 meter per second squared. Let me write the unit also. This is meter per second squared. Now from here force comes out to be as 60 Newton, which is equals to 10 pounds, right? So the force exerted by the person is 10 pounds. Now I don't know you guys have noticed or not, I have not considered the gravity force. I should have been taken it, the gravity force for the ball in the downward direction, but I have not considered. And the reason is, if you see the weight of the ball in the downward direction, it is approximately 1/3 of a pound, and the force exerted by the person is 10 pounds, which is almost 30 times this value. Therefore this approximation is good that we can neglect the gravity force in this problem. So finally the solution is 60 newtons, or you can say 10 pounds. So here in this problem we are given that the acceleration of an object has a magnitude a. Then we need to find the magnitude of the acceleration in the following 4 cases. So first I'm going to represent the question, what the question is saying. So we have an object, its acceleration is a and mass is, let it be m. So acceleration we know it is sigma f net, the net forces acting on an object divided by the mass. This is what we studied in the Newton's second law of motion. Now next in the a part it says that what would be the acceleration if all the forces acting on an object is doubled. So if the forces are doubled, so acceleration this a1 would be 2 times sigma f net divided by mass remains the same. So that is, from here we can write that a would be 2 times a. So acceleration will also be doubled. Now next in the b part it says that the mass and the net force acting on the object are doubled. So mass is also doubled and the net force is, this is also doubled. So this 2 and 2 will cancel and the acceleration will remain the same. So in this case acceleration will remain the same. Now next it says that the net force is doubled and the mass is halved. So acceleration A3 we can write, this is force is doubled, so 2 times sigma F net we can write, and mass is halved, so 1 over 2m, and that is equals to 4 times A. So the acceleration will increase by 4 times. And finally D part you can do on your own, I'm just writing the answer. A4, this would become 1/4 of A. This time it will become 1/4. Okay, now we are all set to study the Newton's third law of motion. Okay, so the Newton's third law of motion. Now we have studied about forces, its effect, the Newton's second law and all that stuff. But here the thing is, nature never produces just one force at a time. Forces always comes in pairs. Further, the forces in a pair acts on a different bodies and are equal in magnitude but opposite in direction. This is what the Newton's third law of motion say. And if you study the statement given by the Newton is, for every force that acts on an object, there is a reaction force acting on a different object that is equal in magnitude and opposite in direction. And in short, we say that for every action there is equal and opposite reaction. For example, here a person pushes a refrigerator. So this will be a direction of force by the person on the object. That is the action. Then the refrigerator also applies the force on the person in the opposite direction with the same magnitude. This is reaction. Few more examples is shown here. When the earth exerts a downward gravitational force on the space shuttle also exerts an equal and opposite gravitational force on the earth. Thus, for every action there is equal and opposite reaction. So from the discussed example, we observe that the action and reaction forces always occur on different object. But here you may have a doubt. While drawing free body diagram, we draw only one force for a given object. Yes, because the other force in the pair would appear in the free body diagram of different object. Like here, as the person exerts a force on a refrigerator, so by the third law, refrigerator also applies the force on the person, which you can see in their respective free body diagram. And since action and reaction force acts on different objects, they generally produced different acceleration. Confused? Let's understand this by taking an example. So here in this example, we can see two groups of canoeists that meet in the middle of a lake. Now a person in canoe 1 pushes on canoe 2 with a force of 46 Newton. The mass of the canoe 1 and its occupants is 150 kg. So M1 we can write to be 150 kg, and here M2 we are given to be 250 kg. Now there are two parts in this question that we need to solve. In the A part, we need to find the acceleration the push gives to each canoe and the separation of canoes after 1.2 seconds of pushing. Now first I'll define the coordinate system. So this is a coordinate system, and for my convenience I'm taking origin to be the point where the canoes touch. Then what we can do is we can draw the free body diagram for both the system. So here I'll be drawing the free body diagram for canoe 2, and here I can draw the free body diagram for canoe 1. Okay, so we're going to consider it to be a point object. Then this is the direction of force on canoe 2 from canoe 1. So this is F2 here, and the weight force in the vertically downward direction W2, and normal force N2 in the upward direction, right? This would be the free body diagram. Now there is no motion in the vertical direction, so the vertical forces are balanced. Now in the horizontal direction we have only one force F2. So from the Newton's second law of motion we can write that acceleration in the x direction for canoe 2, this would be sigma F net divided by the mass for body 2. So that would be equals to sigma F net, we have F2. Now one more thing, from the Newton's third law of motion we can say that the magnitude of force F2 will be equals to the magnitude of force F1, and that is equals to 46 Newton, because action and reaction forces are equal but opposite in direction. Okay, so F net we have a 46 Newton divide by m2. M2 for we have 250 kgs. So from here, the acceleration for canoe 2 is 0.18 meter per second squared. Now we can consider the free body diagram for canoe 1. So here this is the point object. Here the normal force would be N1, weight force W1. Now F1 would be in this direction, right? Now again we can use the Newton's second law of motion. So AX for canoe 1 would be sigma F net divided by M1 this time. Now this time this force is along the negative x, so I'll be writing minus F1, and F1 we have 46 Newton. So basically I'm writing minus 46 because it is along the negative x. So divide by mass is 150 kgs. So from here the acceleration on canoe 1, this would be equals to minus 0.31 meter per second squared. So this would be the answer for the A part. Now next in the B part we need to find the separation of the canoes after 1.2 seconds of pushing. Okay, so basically what we're going to do is we'll be finding the final positions of the canoe after 1.2 seconds, and then we can find the separation distance. Okay, so for canoe 1 x2, this would be 1 over 2 a2x times t square, right? So that is equals to 1 over 2 acceleration a2x we have 0.18 that we calculated in the A part. T is 1.2 seconds and it's squared. So from here x2 is 0.13 meter. Then x1, this would be 1 over 2 a1x this time times t square. A1 we have this value 0.31 with a negative sign. So 1 over 2 minus 0.31 times t square is same 1.2 seconds and it's squared. So from here this value comes out to be as negative 0.22 meter. So after 1.2 seconds canoe 2 is here and canoe 1 is here. So this is x equals to negative 0.22 meter and this is x equals to 0.13 meter. So what would be the separation distance? This distance, this would be x2 minus x1. So we can write this delta x. This would be x2 minus x1 and that is equals to 0.13 meter minus of minus 0.22 meter and that is equals to 0.35 meter. So this would be the separation distance. Now what conclusions we can made from this example? Conclusion number 1. Although the magnitude of action and reaction forces are equal, but they produce different acceleration. Here you can see acceleration is negative 0.31 and here the acceleration is 0.18 meter per second squared. So acceleration is different in both the cases. One more thing we noticed, that heavy objects have less acceleration and hence the less displacement. That you can see here. Displacement is only 0.13 for the canoe 2 and the mass for canoe 2 is more, that is 250 kgs. So more the mass, less the acceleration and the less is the displacement. Now think what would happen if heavier canoe is replaced by a large ship of great mass. So in that case both objects will accelerate, but the acceleration of large ship will be so small that it would appear as large ship did not move. In fact both object will move. Okay, now I'm making a small change to this example that we discussed, and the change is if the canoe 2 is replaced by 25,000 kg ship, rest everything remains the same, then we have to find the acceleration for both the objects, and you have to do this question on your own and you have to write the answer in the comment box below.